Hello students, welcome to the course Illumination Engineering. Myself Milan Sasmol from Department of Electrical Engineering from JIS College of Engineering. So in last class we have seen what are the lights and how they are dependent on the wavelength and how we can visualize the light. And today we will see the details of electromagnetic waves or the details of lights. It means how their energy is dependent, how their wavelengths and frequencies are dependent, and what are their different frequencies. Okay. So at the first, if we consider the what is electromagnetic waves, if we consider the electromagnetic waves, how they are formed, how the electric charge produce that electromagnetic waves, and what are their properties. These are very important for us for this particular course, Illumination Engineering. So electromagnetic waves means that do not need any matter to transfer energy. It means electromagnetic waves means the energy, and if we consider the energy doesn't require any medium to travel or any medium to transmit from one place to another place. It means through the vacuum they can travel also. And obviously these electromagnetic waves, they are made by vibrating electric charges and can travel through space by transferring energy between vibrating electric and magnetic fields. So obviously if we consider the lights, the light means it's an electromagnetic waves. It means there will be electric waves and as well as there will be magnetic waves. So altogether these two waves, they can travel through vacuum also. And the next is, how do they move actually? Any moving electric charge that is surrounded by an electric field and a magnetic field. It means any moving electric charge, that means we can say it's a current, that we can say, we can say it's an electrons, that moving electric charge, right? And that flow of electron, that we can consider as a current, if we consider that as a current, and obviously it's surrounded by an electric field and as well as a magnetic field. And here the arrows symbol that is given there, that is electric field and magnetic field separately. And a changing magnetic field creates a changing electric field, that we know, that if there is a rate of change of magnetic field, and obviously if there is a conductor, obviously it will create any changing electrical field. And one example of this transform obviously, which transfer the electrical energy from one circuit to the another circuit also. And obviously it will having three different portion, we can say, in the main coil, which changing the electric current, which produces the changing magnetic field. So one coil obviously which having some currents and which then creates a change in electric field in another coil, producing an electric current, and obviously the reverse, that is also possible. It means if one coil having some current, it can produce some amount of magnetic field, and when this magnetic field reacts with the another coil, and it can create some amount of electric current, that we have seen in case of the mutual inductance, how the voltage is generated, that we have seen in our circuit theory lecture. The same thing is here. There is no more differences. And if we consider uh, these electromagnetic waves and having the lambda, that is the wavelength, lambda, that is considered the wavelength. And electromagnetic wave means there is one electric waves and one magnetic waves. Electromagnetic, it means one electric field and one magnetic field. The colors, the yellow colors, that defines the electric field, and which is we have considered as our xy axis, and similarly we have considered as a magnetic field, that is our in normal x in our x plane, so we can consider that these two fields, this electric field and magnetic field, they are perpendicular to each other, and as they are perpendicular to each other, and with this perpendicular manners, they are just simply traveling in forward direction as per the direction of this arrow, axis direction arrow. They are moving in forward direction, and always they are perpendicular to each other. And when the electric charges vibrates, the electric field around it changes, creating a changing magnetic field. That we already know. And the magnetic and electric fields create each other again and again, and this process happens continuously. It means one electric fields are there, it creating the magnetic field, again by this magnetic field creates an electric fields, and this procedure, it's continuously, it's happening continuously. Okay, and as a result an EM waves travels in all direction and in any other direction, and the figure shows that the wave traveling along in one direction is given as an example over there, and similarly they can travel in any of the direction. The electric and magnetic fields vibrates at right angles to the direction of the wave travels, so it is a transverse wave. So this is one of the properties of the electromagnetic waves, they are transverse wave. It means the direction, on the direction it's propagating or it's following its forward direction, the always the electric waves and or the electric field and the magnetic field, they will be perpendicular to each other, and this is one important property of this electromagnetic waves. And as a properties of electromagnetic waves, we can say all matter contains charged particles that are always moving, therefore all objects emits electromagnetic waves. Similarly, the wavelength becomes shorter as the temperature of the material increases. So here is a relation between wavelength with the temperature. And electromagnetic waves carry the radiant energy. And if we consider the speed of electromagnetic waves, what is the speed? The already we know the speed of light, that is 3 into 10 to the power 8 meter per second. 10 to the power 8 meter per second, and if we consider it meter per second to kilometer per second, it comes that 3 lakhs kilometers per second. That is the speed of light, obviously in vacuum, speed of the light. And if we consider the speed of this light or this electromagnetic field with the different mediums, then they having the different speed, and the speed of this electromagnetic wave, that is the maximum for vacuum, and similarly if we goes for another medium like air, water, glasses and diamond, then they are at different speeds. Like as vacuums, it having the 3 lakhs kilometers per second the speed. Similarly for air, the speed is less than 3 lakhs kilometer per second, and obviously in water, as the density of the medium that is increases, so obviously its speed decreases. So the water where the speed is 2,26,000 kilometer per second, and glass it comes to it decreases to 2 lakhs kilometers per second, and in diamond it again decreases to 1,24,000 kilometer per second. So in different medium, this electromagnetic waves it having different speed. So this maximum speed, that is in vacuum, and that speed is 3 lakhs kilometer per second, or we can say 3 into 10 to the power 8 meter per second. And obviously that is written over here that electromagnetic waves, that is usually travels in fluids, in the solids, and fastest in glass. If we consider in solids and the glass, and there we can say that the different types of speeds, and as already we have discussed different types of speeds in different medium, so I think it's clear to us that what will be the speed, or how the speed will varies with the different types of medium, right? And the next is, what is the wavelength and frequency of an electromagnetic waves? The wavelength is equals to the distance from crest to crest. It means the peak to peak distance, that is called the wavelength. Or similarly, simply we can say the wavelength means the distance of one cycle, that is called the wavelength also, or peak to peak distance, or that will be same. Or suppose the peak to peak distance, or one zero crossing point to another the next return, when the wave returning into the same points, It means suppose one wave is starting its journey from 0 and again it's going to the positive, and we will consider up to the next point when again it's going to reaches to 0 and going to positive again. So this distance can be also called as a wavelength. Or similarly, the peak to peak distance or the crest to crest distance can also be considered as a wavelength. And the frequency is the number of wavelength that passes a given point in 1 second. That is considered as a frequency. It means in 1 second how much wavelengths are there, or in normally in case of sinusoidal waveform that we have already seen that frequency means in 1 second how much cycle it completes. That is called as a frequency. The same thing is over here also. Okay. Now, as the frequency increases, the wavelength having some changes. Now the question is, how will be changes? Is it increases or is it decreases? What can we say? As the frequency is considered, that frequency is equal to number of wavelength that passes a given points in 1 second. So 1 second how many wavelengths are there, or how many cycles are there, that is in a frequency. So how their relation in frequency and wavelength, is it increase or decrease? So let's think. Yes, it's smaller. It means if frequency increases, the wavelength will be smaller. It means frequency increases means in 1 second the more numbers of cycles are there, or more numbers of wavelengths are there. So the time is fixed. So the time window is fixed 1 second. So in 1 second, it's if the number of wavelength increases, so obviously the length of this wave or the wavelength, that length should be decreased. That's why it's written the frequency increases and the wavelength decreases. And in vice versa also, if wavelength increases, the frequency decreases. And the next question is, can wave be a particle? In 1887, Heinrich Hertz discovered that shining light on a metal caused electrons to be ejected. So we get the electron, that is in 1887 by Heinrich Hertz. Whether it's or not, electrons were rejected dependent upon the frequency, not the amplitude of the light. This is the main important thing. So these electrons, how much electrons that were ejected from this surface or from this place, that is depends upon the frequency, not the amplitude of the light. And the energy, that how much energies will be there, that depends upon the amplitude. So whenever we are considering one electromagnetic waves or any waves are there, obviously it will some few main things are there. One is its wavelength, or we can say its cycle. Second one is frequency, and we have seen the relation between wavelength and frequency, and similarly it will have some amplitude. So based on this amplitude, it will have some energy. So its energy for a particular waves, that depends upon its amplitude. But if we consider that if any from any metal some electrons are ejected from that amounts of electron, that will depends upon the frequency of that waves, not by the amplitude. And amplitude that is responsible, what will be the energy. So energy that is related with the amplitude, and number of electrons which is coming out from that particular metal, which is based on the frequency. So why we are taking all these things in our illumination engineering subject? Because in our illumination subject we will go forward for different types of lights. It means how lights are generated, and only we know the lights can be generated if from one place we can emit some electrons, and as a result if we can get some ultraviolet ray, and as already we have seen that ultraviolet ray having a particular range of wavelengths, and if we can convert that ultraviolet ray into a visible ray, that means we can generate light, or we can get some light from there. So that's why this frequency, this amplitude, and this wavelength, this is very, very important. And obviously after 1887, uh, the few years later, Albert Einstein explained the Hertz discovery. It means electromagnetic waves can behave as a particle that called as a photon. So before Albert Einstein, we don't have any idea regarding this photon, and obviously the Einstein explained us that this photon whose energy depends upon the frequency of the waves. And before Einstein at 1884, that we considered that number of photon that numbers of electrons which are coming from the metal, that is based on the frequency, and the energy over there in that electrons, that is based on the amplitude. And but few years later, the Albert Einstein discovers this thing, and it comes to the front that electromagnetic waves can also behave like a particle, and that is called as a photon. And for this photon, the energy depends on the frequency of the waves. Now the question is, can particle be a wave? This is the reverse thing. The first one is the, can wave be a particle? The answer, we got the answer by Dr. Albert Einstein. Now the question is, can particle be a wave? The electronics field at two slits, that's actually from an interference pattern similar to patterns made by waves. And the electrons which are fired at two slits and actually form an interference pattern similar to the pattern made by waves. So it means if we can fired an electron and which is slits to different parts, and after they creates a pattern, particularly a pattern, and that pattern is very similar to the waves. And the next, if we can consider the electromagnetic waves, and up to this we have seen the electromagnetic waves, how they formed, what kind of waves, different kind of waves, and sometimes they behaves like as. And we know that waves that made by vibrating electric charges that can travel through space whether there is no matter. And what kind of waves? That this kind of wave that is traverse with alternating electric and magnetic fields. It means electric field and magnetic field, they will be in perpendicular to each other based on their direction of propagation or their direction of movement, or the direction of moving, or direction of propagation, that is better. And sometimes they behaves like a waves or as a particle. So this is the most important thing or most important characteristics for electromagnetic waves, or if we consider as a light, that they can behaves like a waves or they can behaves like a particles also. And when they behaves like a particles, they are called as a photons, and when they behaves like a waves, we can consider it as a electromagnetic waves, right? Okay, so that's all for the class, and next we will discuss in our later. Okay, thank you. Okay, so now what is electromagnetic spectrum? If we consider the electromagnetic spectrum, it is nothing but the range of colors of light. It means for different colors having different range of wavelengths. In our class 12 standard, we have seen some basics color about a thing that is visual, and based on the wavelength we can see the different colors. So here the one color spectrum is given, and based on which we can identify in our, or we can visualize that this is nothing but a red, yellow, green, blue, violet, like that. And if we consider the electromagnetic spectrum, then spectrum is nothing but a range of radiation. It means if we consider the wave as a continuous function, means a particular thing which having the different wavelength and different frequencies. As having the different wavelength and different frequency means, if we consider the frequency is nothing but a, if we designed as a n, so n we can say n is equals to, n is frequency, that is 1 divided by the wavelength. Wavelength means the time duration, for a particular cycle, if we consider. So if we look the picture carefully, so at this range we can clearly identify here whatever the spectrums are there, these spectrums having a very less wavelength. And if wavelengths are very less, so and if we want to find out the frequency, and frequency will be obviously 1 divided by wavelength if we consider, so obviously we will get it as a very higher one. So for this region, the having spectrum having very high frequency, and gradually whenever we are moving in the right side or in forward, our wavelength which increases, and as a result the frequency decreases. And we can see the different the wavelength for the, that is 10 to the power minus 13 centimeter in order, 10 to the power minus 13, 10 to the power minus 9, 10 to the power minus 4, 10 to the power minus 6, 10 to the power minus 4, and like that, and similarly goes on. But the main question is, what is that portion that which we can visualize? That it means we cannot visualize very high wavelength of frequency. Similarly, we cannot visualize the lower wavelength of lights. So there is a particular range which we can visualize. So we have to know that which one is important for us and which we can visualize. So if we analyze the previous picture very carefully, we can see that electromagnetic spectrum having the different range of suppose 10 to the power minus 15 centimeters or less than that, to it may happen that 1 centimeter to 1 meter to more than that, whatever. So the picture clearly says that if we consider the gamma rays which having the wavelength in the range of 10 to the power minus 13, 10 to the power minus 13, which we cannot visualize. Similarly, if we consider the X-ray that having the wavelength of 10 to the power minus 9 centimeter range, that also we cannot visualize. Then comes ultraviolet ray in the order of 10 to the power minus 7 to 10 to the power minus 6 centimeter range of wavelength. Then comes our visible light, it means which our eye can visualize. So this visualize light spectrum, or this visualize electromagnetic spectrum, this is nothing but having the wavelength in the order of 10 to the power minus 4 centimeter and plus minus something. And after that, if the wavelength again increases, we are getting the infrared, then again we are getting microwaves, and then we are getting the radio waves. So one thing is clear that the electromagnetic spectrum which having the different values of wavelength, and based on these different values of wavelength, they have the different application, like or different names basically, like gamma ray, X-ray, ultraviolet ray, visible light, infrared, microwaves, radio waves. And if the wavelength are changing over there, similarly their frequency is also changing. And not only the frequency, as their wavelength is changing, and we know the formula, that is E is equals to h nu. By using that equation, we can say by changing their wavelength, their energy is also changing, right? Now we need to know some properties of that electromagnetic waves. We can say that electromagnetic waves, they are transverse waves, and they do not require any medium. It means whenever these waves, electromagnetic waves as a light, they are traveling from one place to another place, and then if there are any medium or not, it doesn't matter. So it can traverse without any medium, and if there are any mediums, then obviously it may be absorbed, it may be reflected, it may be refracted. So that is based on the medium. But if there are no more medium, the light can smoothly travels from one place to another. Thus we can travel, thus we means the light can travel through the vacuum. And if it can travels through the vacuum, obviously it will have a speed. So this speed, the speed at which this electromagnetic wave travels, that speed is called the speed of light. And already we all of we know that the speed of light, this is nothing but a 3 into 10 to the power 8 meter per second, obviously in vacuum. So if, and we know the light which is the which having the maximum, the topmost speed in our world, and nothing is there which is greater than this speed. And can you imagine this speed, that is 3 into 10 to the power 8 meter per second speed in the vacuum also. Okay. And if we want to use these electromagnetic waves in our daily lives, we can simply say one thing, that our daily lives is full of electromagnetic waves. For every place there are these electromagnetic waves are present over there. If we consider the TV station to our living room, and always there's there. If we consider our radio, it obviously it works on the radio waves. Similarly, if we consider the microwaves, there are also microwave frequencies are there. Similarly, if we consider the infrared, suppose in a few days back we used to transmit our some data by using this infrared, right? So there infrared frequencies are used to data transfer. Similarly, the ultraviolet, and we know that this ultraviolet or UV rays, they are used to disinfectant in things, or to kill any bacteria or viruses. So where we can use this ultraviolet rays. Similarly, for the X-ray, suppose there are any broken parts of human limbs, or broken parts of in our body, so obviously the doctor refers us to go for the X-ray plate, and so that they can understand that which parts is broken. And every of us that we follow this instruction, and that X-ray, which is nothing but use of this electromagnetic waves. Similarly, the gamma rays, which are used to kill the, or to sterilize the cancer cell, which is very dangerous in our for our body. So as a conclusion, we can say one thing, that these electromagnetic waves are, we are surrounded by these electromagnetic waves from our daily life to most of the important means for surgical things also. It means for our treatment, for our surgery, for our daily life, for our cooking purpose, every places we can find these electromagnetic waves. And as a conclusion, we can say, or we can refer these slides as a the application of these EM waves. And already we have discussed this application of EM waves in radio waves, microwaves, infrared, visible light, ultraviolet or UV ray, X-ray, gamma ray. So whatever the frequency, so all these differentiation, that is based on their wavelength or based on their energy. Now we'll see few examples by where we can use this. This is radio that we all know, that in this radio we can use these electromagnetic waves. And similarly, this is also our previous days television, that we all know that these two types, these antennas are over there, and by this antenna it's communicate with this sender to receiver ended. Similarly, we are very much very familiar with these mobile phones, and in this 21st century also we can say it's an mobile era, obviously. So there is also the electromagnetic waves in our cellular phone, basically in telecommunication system. And the next is our microwave. Similarly, for the satellite communication, there also we use these electromagnetic waves. and infrared, obviously, to control anything in remotely. For TVs, ACs, whatever we can control remotely, where we use these types of remotes for TV, DTH, home theater, AC, anything. There we use this infrared. And this infrared that are not only used for this remote system, that are not only limited. This infrared can also be used for taking the photographs. And we know for the satellite communication or any other thing types of communication which is remote communication, for there we use this infrared or other types of rays also to take the photographs also. So there is one another application of this infrared.